We have a ladder of mass M and length L, and it's leaning against the wall. The wall is frictionless, and the coefficient of static friction between the ladder and the ground is mu. We want to find an expression for the minimum angle at which the ladder can lean without slipping. I'm going to further extend this and say we're going to find an expression for the minimum angle in terms of only mu. So that's not written in here, but we're going to go that far, okay? So let's go ahead and start by drawing a diagram. So we have our wall, and we have the ground, and then we have a ladder. So we have a ladder here, and this ladder is going to make an angle theta with the ground. Okay, so we have some forces working here. It also doesn't specify that the ladder is uniform mass, but we're going to go ahead and make that assumption. So we have 4 forces. What can you guys tell me? All right, where from? All right, so we have a normal from the ground, so I'm going to put that here. And then I'm going to put normal G, and then we have a normal up here from the wall. Now remember, normal force is always perpendicular to the surface, so that's going to go this way. So we have normal from the wall. What else? And the weight force is going to be in the middle center of mass, because we're going to assume that this is uniform. And what else? And then friction on the ground, not to be confused with friction on the wall, which does not exist. Okay, so this is friction here. So we have these 4 forces. Now the ladder is leaning without slipping. And what does that tell us about our net force? So we have the net force equals 0. And because of that, we can look at our 2 directions. So net force is made up of your x component force vectors, your y component vex forces. So in the x direction, since the net force is 0, what equation could I set up? Equals the static friction F. Good. And what about for the y? The weight force equals the normal force of the ground. Okay, so this is what we know about the forces. The other thing we can do too, I'm going to add an equation in here. So we're going to put a star here. We also know another equation for friction. And what is that equation? It's going to be mu, and then the normal force from the ground. But what does the normal force from the ground equal? So this is going to be mu mg. Okay, good so far? All right then. So let's go ahead and go to the next thing we want to look at. And if this were to slip, okay, if this were to slip, then we would have some sort of rotational motion. Okay, so we know that this is not rotating, and therefore, what is the net torque? The net torque equals 0. All right. Now, because this ladder is in static equilibrium, and it's not slipping, all right, we can actually pick any pivot point we want on the ladder. Now, if it were actually turning and actually spinning, we would have to pick the point at which it was spinning. Does that make sense? Like, we would have to know that. All right, but in this situation, since it's not in motion, we can pick it wherever we want. That's the advantage to our static equilibrium problems. Now, what is going to be the most advantageous spot to pick our pivot point? Right here. Why? It is closer to the ground, but why is that helpful for us? What is that going to do for us to help set up equations for solving? what do we know about the torque at the pivot point? The torque at the pivot point is 0. Okay, now that's really helpful because how many forces do I have at the pivot point right here? I have 2, so when I'm setting up equations, and I'm setting up torque equations specifically, I can make the torque caused by the normal force of the ground 0, and now the torque caused by the friction force at the ground is also 0 because their radial distance away from the pivot is 0. So when I'm setting up my net torque equation, I really only need to take these 2 forces into consideration when setting up that equation. All right. Now, if I pick the pivot point to be here, then I would be using all 4 forces. If I pick the pivot point to be right on the weight force, then I would have 3 expressions or three terms for the net torque formula. Do you see what I mean? So you can pick, if I picked it here, that would eliminate this. The torque caused by the normal force would be 0, so I would just have to add up these 3 torque values. All right, but by putting the torque here specifically, all right, so we are going to pick as pivot so that the friction and the normal force from the ground are not needed for the net torque equation. Okay, because if you guys remember, net torque, if it's 0, the sum of all the torques working on the ladder have to equal 0. Well, if these are already 0, we don't even need to look at which way would make it turn and whatnot because that's where we've identified our pivot to be. We do need to, however, take a look at this one. So, so if this is my pivot, and I have my pen here. Okay, here's my pivot. This is going to be clockwise. And if the weight force is my pivot, right, and I'm pressing, oops, wrong way, and I'm pressing down, then what direction does this go? Counterclockwise. Okay, and because the net torque is 0, what do I know about these 2 torques then? They're going to be equal. Okay, so what's going to happen is I need to identify the torque caused by the normal wall force, and that's going to be equal to the torque caused by the weight force. But we have 3 pieces of information that we need. All right, for torque, we need the radial distance from the pivot. We need the force value, but we also need the angle that the force makes with the radial distance. So let's take a look at that next. Okay, so we have this known value theta, and by known, it's not known, that's what we're trying to find. But if I identify this is theta, the angle from the ground, what do I know about the angle that the normal force makes with my radial distance? That is also theta. Okay, and the reason why this is also theta is because they're alternate interior angles. This is parallel with the ground. Okay, and alternate interior angles are congruent. So if this is theta, this has to be theta. But here's the thing, everybody see this? Now if I extended this line caused by the weight force, I'm looking for this angle here. I'm going to call this beta. All right, so the angle that the weight force makes with the radial distance here is beta. The problem is I'm trying to solve for theta, so I don't want to have a different angle. So we can either write 90 minus theta, but then we get into some big trig identities that most of you probably are trying to forget as fast as you learn them. But let me show you guys something for a second. So this is a little bit of trig review. So if this is my triangle, and I have theta and beta, and I have a right triangle. I'm going to call this A, B, and C. Now we're trying to solve for beta, and I know that sine of beta equals B over C. Everybody agree? So opposite or hypotenuse. Now watch this. If I'm doing cosine of theta, so here's theta, cosine is the adjacent side, which is b, and then over the hypotenuse, which is c. Okay? So that means that sine of beta has to equal cosine of theta. Okay? And in a right triangle situation, that's actually always going to be true. Sine of one angle is cosine of the other angle. All right? So anytime you have complementary angles, that's the situation. So using that idea, right, for the torque here, the torque for the weight force is going to be, over here, it is half of the length of the ladder. So 1/2 L is my radial distance. And then it's the force, which is mg. So here's R. Here's my force, mg. Normally, I would say sine of the angle with the radial. So I want to say sine of beta. But because I'm trying to solve for theta, instead I'm going to put cosine of theta. So cosine of theta is sine of beta, where beta is the angle from the radial distance. So that's a little bit of trig review for you guys. So coming back to this guy, though, this is much easier because it's already in terms of theta. It's the total length of the ladder. So I have the length of the ladder times the normal force from the wall times the sine of theta. All right, now what's nice here, what cancels out right away? The L values, super convenient. Trig identities, I have two trig things, sine and cosine. How can I combine them into one? Too much, too hard. We could, but that's too much. If we divide both sides by cosine of theta, sine over cosine equals tangent theta. All right, so now I have one trig function instead of two. Good so far? All right, so I have tangent of theta. That means what I want to do, I also want to remove this normal force from the wall. So what happens is I'm going to leave the mg on top, and this 1/2, I'm going to put the 2 on the bottom times the normal force of the wall. But like I said at the beginning, my goal is to solve for theta in terms of just mu. And I have mg, and I have the normal force of the wall. But let's take a look over here, you guys. So we're looking at the forces, and notice the normal force of the wall is equal to what? To friction. But wait, friction equals mu mg. So now we're just going to do a substitution. So we're going to take the normal force of the wall equals friction, right? And friction is mu mg, and we're going to put then the normal force equals mu mg over here. So this becomes mg over 2 times mu mg, and then obviously what cancels out? The mg's. And so I'm left with 1 over 2 mu. What is a final step in solving for theta? Take the inverse of both sides. So tangent inverse of 1 over 2 mu is going to be the value for our theta here.